Okay, so today we're going to learn how to use dummy codes. A couple learning objectives. You're going to understand why dummy codes are needed, learn how to create them, how to include them as predictors, and how to interpret the output and write up the results. We're also going to look at um, a model where we include a covariate, and that can be generalized to a model that includes multiple other predictors. Okay. When do we need dummy codes? Dummy codes are used when the predictive variable is a nominal or a qualitative grouping variable. And that's really a variable where the response options do not exist along a quantitative ordering. I've got three examples here: sex at birth, female versus male, political party affiliation in the US, Democrat versus Republican versus independent, and hypothetical country of origin variable that we're going to use as the example in the slides. And we've got four countries here: USA, China, the United Kingdom, and Colombia. Okay. At the top of this slide, I've got two tables showing the four countries. Each country here has 25 hypothetical participants. And the group variable shows how the countries are coded quantitatively on the data file. So in the first configuration, China gets a code of 0, the US gets a code of 1, the UK gets a code of 2, and Colombia gets a code of 3. The entries in the outcome column are a hypothetical average measure of collectivism for the sample in question. And the table on the left has one ordering of the countries, 0 through 4, with China being assigned 0 and so on and so forth. The table on the right has a slightly different ordering of countries. Okay. Below each table, I've got a figure. In the figure, the country of origin is plotted on the x-axis, collectivism, or our hypothetical outcome variable, is plotted on the y-axis. The black line in the figure tracks the observed means in each of the country groups, okay? And then the red dashed line codes the linear association between x and y. And in the figure on the left, we can see that the linear association between x and y is pretty flat, functionally 0. In the coding on the right, the linear association between x and y is strong and positive. Okay, so what is the problem with juxtaposing these two figures? Well, assigning countries to response options is arbitrary, right? So we're going to arbitrarily choose a country to code 0 or 1 and so on and so forth. Okay. Now, when we've got a qualitative or nominal grouping variable and those quantitative response options are arbitrary, it doesn't really make sense to think about a linear association between x and y. However, if we include the original categorical variable in the regression model, that's exactly what the model assumes. Okay. So now the solution to this problem is we want to try and represent that information in a more qualitative way. And we could use one of several coding systems to do that. The coding system I'm going to be talking about today is the dummy code system. Dummy codes are one or more codes, and these codes will actually become variables on the data file that are then included as predictors in the regression model. The analyst must create G minus one dummy codes, where G is the number of levels of the categorical predictive variable or the number of groups associated with the variable. In today's hypothetical example, we've got four country of origin groups. So we're going to need 4 minus 1 or 3 dummy codes to include in our analysis. Okay. Now, when we create the coding system, we're going to designate one of the groups as the reference group. The dummy codes will then compare each of the remaining groups to the reference group. And in today's example, I'm going to use the USA as the reference group. Okay, so here is the original coding on the left-hand side. Here we've got the original coding of the country of origin and the original variable named group. And then on the right-hand side of the table, I've got the three dummy codes. One is named China, one is named UK, one is named Colombia. And so each dummy code contrasts the country in question with the remaining groups, right? So the China contrast, China gets a 1, the remaining groups get a 0. For the UK contrast, the UK gets a 1, the remaining groups get a 0. The Columbia contrast, COL for short, uh, the Columbia group gets a 1, everyone else gets a 0. And then the reference group, the USA in this case, is going to have a 0 across all three dummy codes. Okay. Now, when we put these three predictors, China, UK, and Columbia, in the regression model and partialing takes place, the dummy codes create pairwise comparisons between the group in question and the reference group. Okay. So the China code will contrast participants born in China to those born in the USA. And there are lots of different ways you could name the codes. I like to name them so that the name of the code signifies the contrast that's being captured by the code. Okay. Now, I'm going to show you how to run the analysis using SPSS software. It's a common software package used for analyses in the social sciences. And there are lots of different ways, again, you can create dummy codes. The way I do it here is I use 3 compute statements to initialize our 3 new variables. And I give everyone in the data file a value of 0 across all 3 codes. And then I use 3 if statements to take the group in question to turn that group to 1 on their dummy code. So in the original group coding system, the 0 group was China. So I say if group 1 equals 0, China equals 1. And then the UK was coded 2. So I say if group 1 equals 2, UK equals 1. And then Columbia was coded 3, same thing. And then on the right-hand side here, I give a caveat that when you use a variable initialization procedure like this, it can get a little tricky handling missing data. So if you download the syntax file, you'll see that I've got some syntax in there to deal with the possibility of missing data on the original country code. Okay, at the top of this slide, I've got some syntax that we would use to run the regression. The stat subcommand is asking for some output. The def subcommand just declares the DV as collective 1. And then the method equals enter statement specifies the predictors that are being entered. In this case, the model is comprised of the 3 dummy coded predictive variables, China, UK, COL. Okay. In the model summary table, we get the R squared here. It's 0.301, suggesting that inclusion of the 3 predictive variables accounts for 30.1% of the variability in collectivism. And then the ANOVA summary table gives us a test of whether or not the overall model is statistically significant. So we would say F on 3 and 96 degrees of freedom equals 13.76. P is less than 0.001, suggesting that those 3 dummy codes are accounting for significant variability in the outcome. Next, let's take a look at our coefficients table. I'm going to direct your attention to the unstandardized coefficients here because this is carrying information that is related to the mean differences between each of the 3 remaining countries and the reference group. And each code is evaluated for statistical significance. And so when a dummy code is significant, it suggests that the pairwise contrast implied by that code is consistent with a significant mean difference between, in this case, China is statistically significant, suggesting that the mean difference between China and our reference group, the USA, is significant. And the same is true for Colombia. And then the contrast between the UK and the USA is non-significant. Okay. Now, we could also use the unstandardized coefficients to derive the means for all of the groups. Okay, so the constant, which is the y-intercept in the model, reflects the predicted y when all x's are equal to 0. So you might remember that that is true for the reference group only, and so the y-intercept captures the model implied average on collectivism for the USA group, and in this case it happens to be 6.75 because each dummy code reflects the mean difference between the USA and the country in question. We can use those codes to solve for the mean in that country, which I present explicitly on the next slide. Okay, so I mentioned before that the USA mean is going to be the constant, 6.75. The China mean is going to be the constant plus the China coefficient, so 6.75 plus 5 gives us a mean of 11.75. The UK mean is going to be the constant plus the UK coefficient, so in this case it's going to be 6.75 minus zero point 0.5, which will give us 6.25. And then the Columbia mean is going to be the constant plus the Columbia coefficient. 6.75 plus 4.75 will give us a mean for the Columbia group of 11.50. Now, I don't explicitly show how to derive these means, but essentially we would lay out the constant and the various x beta pairings. And for the USA group, we would have the constant, and then for the China, UK, and Colombia codes, the X value for the USA group would be 0 across all three codes. And so all of these coefficients would go to 0, leaving only the constant. For the China code, their regression equation for the average in the China group would be the constant plus the China coefficient times 1. And then these other two codes would drop out because the individuals in China are coded 0 on the UK code and also 0 on the Colombia code. And so that just leaves the constant and the code for their country. The same thing would be true for the UK and Colombia. Okay. All right. So here's how we might write up the results in this case. We'd say, okay, we use multiple regression to test whether individuals born in 4 different countries reported different levels of collectivism. We use 3 dummy codes to contrast all remaining countries with the United States. The reference group in the analysis, for example, the China code contrasts China to those individuals born in China to those born in the USA. And here's some technical statistical information. The overall model was statistically significant. There's some technical statistical information. F on 396 degrees of freedom is 13.76. P is less than 0.001. R squared equals 0.30. Both China and Colombia reported significantly higher levels of collective orientation relative to those born in the United States, and the mean differences were large in magnitude. And then for the individual coefficients, the technical statistical information is the unstandardized regression coefficient, its standard error P. And then I used a Cohen's d as the effect size estimate because here we're talking about mean differences, and Cohen's d is just a very natural metric when we're talking about mean differences. You might remember your interpretational guidelines for Cohen's d. 0.2 is small, 0.5 is moderate, 0.8 is large, and d is interpreted in absolute value because it can take on both positive and negative signs. Okay. Now, when we use ANOVA in a situation like this, the program transforms the original categorical variable into a set of codes, like effect codes, behind the scenes. And now you know why that happens. Okay. Now, I want to look at a scenario where we add a single additional predictor. We're just going to use the generic term covariate to describe the single additional predictor. And what I'm talking about here can generalize to a scenario where we add multiple predictors. Okay. So here we're going to add the covariate. We're going to assume that the covariate is moderately correlated with the outcome with an R.356. And the multiple correlation between the covariate and the country codes is 0.245. Okay. So now when we add the covariate, we can examine 2 things simultaneously. We could examine whether or not the country codes account for significant incremental variance in collectivism over the effect of the covariate. And we could also examine whether or not the covariate accounts for significant incremental variance in collectivism over the country codes. Okay. Now, because we've got 3 dummy codes capturing contrasts among our 4 countries, I'm going to use a hierarchical regression analysis so we could get the incremental variance of the test of the codes, and then we could also get the various pairwise contrasts. And so let me sort of show you what I mean. If you're not familiar with hierarchical regression analysis, it's a way to structure a regression model as really a series of models that are built sequentially or hierarchically. And in SPSS, we're going to have as many method equals enter statements as we have predictor blocks. In this case, we've got two predictor blocks. We're going to put the covariate in on the first predictor block, and then we're going to add our three country dummy codes on the second predictor block. Okay. Now, in our model summary table, if we request that SPSS prints out the change statistics, we're going to get the R-squared change associated with the addition of the country codes. In this case, the R-squared change is 0.239, suggesting that the country codes account for an additional 23.9% of the variability in collectivism over the effect of the covariate, and that incremental variance is statistically significant based on this F change statistic. Okay, so here in this sort of middle bullet point here, I give the technical statistical information that points that out. And I talk about the proportion of outcome variability attributed to the country codes. Now, if we look in our model 2 coefficients, then we get the pairwise differences between each country and the USA, which is the reference group. Now these pairwise differences are adjusted for the presence of the covariate, okay? And so the two codes that were significant in the original run remain significant. So the China code is statistically significant. The Colombia code is also statistically significant, okay? Now, we can, similar to what we did originally, we could use the unstandardized coefficients to help us solve for the means in each of the countries. Now, I grand mean centered the covariate, which means that the average study participant is coded 0 on the covariate. And so we could use the same equations we looked at before to figure out the adjusted group means. And so the USA mean adjusted for the presence of the covariate is going to be equal to the constant from the model 2 coefficients, that's 7.227. And then the China mean would be the constant plus the China coefficient. And so that mean is 11.545. And again, that's adjusted for the presence of the covariate. Okay. All right. The first bullet point here mentions the point I was just talking about, that these pairwise differences among the countries are adjusted for the presence of the covariate. The second bullet point, or the lower bullet point here, talks about how in the model 2 coefficients, we can get a test of whether or not the covariate accounts for incremental variance in collectivism over the country codes. It is statistically significant. And then the effect size estimate associated with the covariate can just be the square of the part correlation, which is the semi-partial correlation squared. And in this case, I believe that 0.255 squared is accounting for about 6.5% of incremental variance in collectivism. Okay. Now, when we think about these kinds of models in the ANOVA framework, it's a little bit more natural to think about alpha inflation, and the software typically has a number of adjustment procedures that we could use to when we test for mean differences. Now, we don't get those alpha adjustment procedures by default in standard regression procedures, and so if we wanted to adjust for alpha inflation, we'd have to do that adjustment on our own. Another point I want to mention when we think about the pairwise contrast, if we have a 4-level grouping variable, there are really 6 unique pairwise contrasts among means. Only 3 of those contrasts were explicitly tested for statistical significance in the original dummy coding scheme. In order to get explicit tests of the remaining pairwise contrasts, we would have to create, in this case, 2 additional sets of dummy codes to represent all of the sort of unique information. And obviously, as the number of groups gets larger, this process can become tedious, which some might think is an advantage of using the ANOVA software for models like these. Okay, a couple of other issues that I wanted to mention. If we wanted to test a country by covariate interaction in the current scenario, we'd have to multiply each dummy code by the covariate. So the overall interaction would have 3 numerated degrees of freedom associated with it. And if we wanted to build that interaction into the analysis, we might again extend our hierarchical regression model, where in block 1 we would include the covariate on its own. In block 2 we would add the 3 country codes. And then in block 3 we could add the 3 product terms. And then the R square change, F change associated with block 3 would be tantamount to testing the omnibus interaction for statistical significance. And then the final point on this slide just says that the interpretations get trickier when there are product terms in the model and a mixture of lower and higher order effects. And that's a discussion that I'll talk about in a separate video. I'm close to having my website up and running, so at some point you'll be able to visit my website, deluciastats.com. There you'll be able to download all the materials associated with these videos, and so I'll put the data file used in this video and the syntax used in this video file there, so you can download, run the analyses, follow along. Thank you for watching. I hope you enjoyed the video, and I hope the next time you need to fit a regression model with some dummy codes, you'll feel more confident in your ability to do that. Take care.